The sliding filament theory explains how muscle contraction occurs at the molecular level through an interaction of myofilaments within a sarcomere. This is the model of the sliding filament theory, and before we get into the relaxed state of the three different stages, we'll first talk about what each block represents in the legend. This white block represents the M line, this black block represents the H zone, this emerald block represents the A band, the gold block represents the I band, and this chain-like structure represents titin. These torches represent trypomyosin. This orange block represents the Z line. This blue wool block represents the thin filaments, which is actin. This dark blue block, this lapis block, represents troponin, which is attached to actin. And then the red wool represents the thick filament, which is myosin. Last but not least is the water blocks, which represent the calcium ions. So going back to the main model. So the sarcomere is the functional unit of a muscle fiber. In the relaxed state, it appears at its maximum length. There's no shortening of the sarcomere. What is consisted in the sarcomere are the myofilaments, so that there's a thick filament and a thin filament. The thick filament, which is myosin. The myosin heads are not actively bound to actin in their relaxed state. However, ATP is bound to the myosin heads, keeping them in their cocked position ready for contraction. The thin filament, actin, the actin filaments are not actively interacting with myosin. The binding sites on actin are covered by trypomyosin, preventing cross-bridge formation. So we can see that. So this blue wool represents the actin, and these torches represent the trypomyosin, preventing from the cross-bridge formation. So the regulatory proteins. Trypomyosin blocks the myosin bonding sites on actin, preventing contraction, which is the torch that was right there. And the troponin holds trypomyosin in place. It has not been yet bound to calcium, so the trypomyosin remains in its inhibitory position, which is the lapis, or the dark blue block that's right here. Zones and bands of the sarcomere. So the Z line, or the Z disc, indicated by the orange blocks that forms a zigzag sort of shape. It marks the boundary of the sarcomere. The thin filaments are anchored onto the Z line. The distance between the Z lines is at its longest in the relaxed state. This I band indicated by the gold blocks, that region. It's the lighter region of the sarcomere that contains only thin filaments. It is at its widest in the relaxed state because the thin filaments are not overlapping with the thick filaments. The A band, indicated by the emerald blocks, is the dark central region of the sarcomere where the thick filaments, the myosin, are located, which is indicated by the red wool. This band's width remains unchanged in the relaxed state because the length of the thick filaments do not change. The H zone, represented by the black netherite blocks, is the central position of the A band that contains only thick filaments and that there is no actin overlap. This zone is at its widest in the relaxed state. The M line is represented by the white blocks. The M line is the central structure of the sarcomere that stabilizes the thick filaments, and it does not change position in a relaxed state. But now there's titin. This is represented by the chains, which we can find right here. This chain structure represents the titin, and titin is this elastic protein that connects the thick filaments to the Z line and helps maintain the sarcomere structure. In the relaxed state, titin is slightly stretched, contributing to the passive tension of the sarcomere. Calcium ions are stored in the sarcoplasmic reticulum in the relaxed state. The cytoplasmic reticulum levels are low, so troponin remains unbound to calcium, keeping tropomyosin in place. Just a summary of everything that has occurred in the relaxed state or that isn't recurring. So right now, actin and myosin do not interact. The H zone and the I band are at their maximum widths. The sarcomere is at its longest resting length. The tropomyosin blocks the actin binding sites, preventing it from contracting, and the calcium remains stored in the sarcoplasmic reticulum.
So, in the resting state, the myosin heads are primed and ready, having hydrolyzed ATP into ADP and inorganic phosphate. This stores energy in the myosin heads, putting them into a cocked position. However, actin binding sites are blocked by the protein tropomyosin. When a nerve signal reaches the muscle, it triggers the release of calcium ions from the sarcoplasmic reticulum. These calcium ions flood the sarcomere and bind to the regulatory protein troponin. So as we can see, the calcium ions have been released, represented by water, and they have removed the tropomyosin from the troponin, therefore allowing for the next stage of contraction, which is the formation of cross bridges of the myosin heads to the troponin. Okay, so with the release of the calcium ions and the removal of the tropomyosin, cross bridges are now capable of being formed between the myosin heads and the troponin. These cross bridges marks the start of the power stroke, and the sarcomere can now be considered to be activated. Okay, so finally the last diagram showing the final stage of contraction. As we can see, the power stroke has been fully completed, resulting in the actin fibers being pulled on and for the eye zone to be shrunken. However, we can see that the A band is completely unchanged, as the thick filaments do not change in this process. However, the H zone has completely disappeared, with the actin basically completely overlapping the myosin heads, the myosin. So after this contraction, we can see that the Z line has now moved closer to the M line. And as we can see through this whole thing, you can see the actual gaps that were created caused by this contraction. And although this one small contraction of the sarcomere may seem small and insignificant, the contraction of the sarcomeres is the foundation of all voluntary movement. From the simplest gestures to the most powerful exertions, this intricate process highlights the efficiency and the complexity of muscular systems. Thank you.